Well, let's get started. I switched a little bit the topic for today because I think it's an important topic to talk about. We're going to need to use these ideas from now on, the idea of normalization. It's not a long lecture, so we're going to have about 10 slides about normalization. So probably you won't cover the whole time of this lecture. So if you have enough time, then I'll actually start talking about recurrent neural networks today. Otherwise, we can finish with normalization. I normally don't like to do that, of having two topics in the same lecture. But I didn't find a best place to fit this in the material. It should be actually in the beginning, I guess, right before multilayer perceptron, or right after multilayer perceptron. But we had that exam there, and we had an extra holiday that I didn't plan for. So anyways, here it is, normalization. So before we get started, announcements. The programming assignment is out and is due on October the 30th, which is next week, or Wednesday, at 11:59, okay? Feel free to ask questions if you have at the end of the lecture. And we were talking about convolutional neural networks last lecture, particularly about pooling layers, classic CNNs, and residual neural networks. So we covered what are max pooling and average pooling in the context of CNNs. Then we investigated a couple of famous architectures of convolutional neural networks, particularly LeNet5, AlexNet, and VGG16. And then at the end, we discussed that idea of residual neural networks, which are those cool skip connections that we can use to form residual blocks and then build much bigger neural networks, okay? But we're going to change topic a little bit today to talk about normalization, which we already did informally. We've been actually using normalization in our assignments in images. If you remember, we've been actually dividing the pixel values by 255 to normalize the images. And that's one type of normalization. Today I want to talk about three types of normalization: input normalization, batch normalization, and layer normalization. Okay? And then if you have time, we're going to start talking about RNNs. So this is what we've been doing so far when we are processing images. And both our assignments so far, actually the three assignments so far, they are dealing with images, right? And right at the beginning of the assignment, there was a line there, or some sort of cell in Colab, asking you to normalize the input image. And in that scenario, normalizing meant dividing the pixel values by 255, right? So we were pretty much doing something like this. We'd grab the image, divide all the values by 255, just to rescale those values to a range that goes from 0 to 1, right? And I wasn't discussing much why do we do that, right? And it turns out this makes training actually faster. Because the values, the input values they're closer to 0, and as we already know, if you have a hypothesis like this, all right, let's actually add an activation function here. All right, if this value here is close to 0, right, this whole value here is close to 0, and then from the sigmoid function, right, you're going to be in this region here where the gradients are bigger, so we're going to have larger steps in our gradient descent optimization. Okay, so that's one benefit of normalizing. It makes training faster. Okay, but this is just a simple type of normalization we can do with images, because they typically pixel values range from 0 to 255, right? So if you just divide all these values by 255, we get a normalized image, right? This is pretty simple, okay? But we have more general ways of normalizing input data in machine learning. So let's consider a different problem. This is a structured data problem. Let's go back to that house price prediction data set. Right here we want to predict the price of a house and with respect to three features: size in square meters, number of bedrooms, and I'm adding a third feature that we haven't seen so far, which is the nearest, the distance to the nearest subway station. So if you live in a big city, that's a very important feature for a house. You want to live close to a subway station, right? Because then you can get to anywhere you want. So that makes actually houses and apartments very expensive in big cities, that particular feature, right? And that is measured in meters. So it's the distance in meters to the nearest subway station, okay? So we have those three input features, x1, x2, x3, and we want to predict the last column, which is the house price or the apartment price, okay? So pay attention here that all these three features, they are in completely different ranges, right? So one is in, because they're units, right? So one is defined in square meters, the other one is defined in number of bedrooms, so it's a unit value, it's an integer. The other one is in meters, so then it has those very large values. So for example, the last example there has 12,000 meters, which is 12 kilometers, right? So it's a house that is very far from a subway station. So that difference in range of these features might make your training much more challenging. And there's a question. No question? Okay. And I'm going to argue why. Okay. It's kind of, you probably have an intuition that this is not a very good idea, right? Having different ranges might not be very helpful for training a model. And the reason why is, let's assume, for the sake of argument, that we are dealing with a linear regression model and stochastic gradient descent. So in linear regression, we start with our weights with zeros, right? So our first W there is 0, 0, 0, okay? And let's assume alpha equals to 0.1. We're not going to do any complicated math here, but just for illustration. So when you're training, consider we're going to process, is a stochastic gradient descent. So you're going to process each example independently, one at a time, okay? Starting the first row, then second row, third row, and so on. And the update rule is W equals to W minus alpha, and then the partial derivative of the loss with respect to W. And we're going to compute those partial derivatives with respect to a single example, okay? So that turns out to be, okay, 0, 0, 0, because that's the definition of, that's how we initialize the weight vector, minus 0.1, which is the learning rate alpha that we have defined arbitrarily. And then the third, the multiplication factor there, y hat y minus y I that times x I, that's the definition of the partial derivative of the L with respect to W. We have seen that before, right? So that we've came up with that formula by hand. That's the partial derivative of the mean square error loss, particularly, right? Because this is linear regression. Good? Okay. So initially W is 0, so if you multiply 0 by 152, then 0 by 4, then 0 by 7,200, you're going to get 0. Plus B equal to 0, so the prediction that we get with linear regression for the first example is going to be 0. So 0, so y hat I is going to be 0. Minus 1,500, or 1,550 it should be, right? Not because this is the price of the first house. Times xy. So simplifying this a little bit, what you get is 0 minus 1,550 minus 0.1, that should be plus. Let me fix this math. It's actually wrong. This should be 1,550, and this should be plus. Okay? So this should simplify to this expression here. So look at look at this, right? We are multiplying now at the end 150 by all those feature values, 152, 4, and 7,200. This is because x that's our input feature x. And we're multiplying the same scalar 155 by those 3 different values. But because that third feature near subway station is in this much larger scale, the changes in W3 here, they affect much more the output than W1 and W2 in this case. Okay. And that's a problem. Why is it a problem? Does anybody have an idea?
Because just the third variable will matter in the output of the model, basically.
Yeah, intuitively that's one good argument. A small change in W3, or a small change in X3, sorry, would affect a lot the loss rate. And a small change in X2 would not affect the loss rate, the loss function very much. So let's visualize that. So when your input data X is the input matrix, right, with all the examples in the columns, when your data set is not normalized, then what happens is your error surface will have very different curvatures along different axes. Okay, so visually you're going to get this ellipse here because now I am dealing with just one W and one B for visualization. Obviously this would be a high dimensional plot, but if you had only 2 parameters, you would get a curve or an error plot like this one. Okay? And see how the curvature on the y-axis, it's wider or larger than the curvature on the b-axis. Okay? So when you normalize your data, what you get is actually you rescale your loss curvature as well. So when you normalize your data, you get this equal curvature between W and B. Okay? And in consequence, what that does to us, so first of all, that makes normalizing the data makes the error surface much more easy to optimize for. Because it's this more kind of well-defined shape, whereas when you have that ellipses there, it's a little bit more tricky to navigate on that surface. Okay? So in practice, what happens is you're going to need more steps to optimize your loss function on the left case where your data is not normalized, and when it's normalized, then you get this very nice looking curvature for both of the dimensions or axes here, and then in practice you can have larger steps or you can take just large steps to get to the minimum. And in terms of implementation, what this means is you can pretty much use larger learning rates when your data is normalized. Okay? So and you can see that in practice. If you can do that experiment yourself. Okay? Try to minimize a loss function when your data is not normalized, and then normalize it and see how you can change the learning rate yourself. Okay? But that's what you get when you normalize your data. So how do you normalize the input data? So what we want to do is we want to have all our examples to have mean equal to 0 and standard deviation equal to 1. So here's an example of a synthetic data set. Here you see there's 2 dimensions, x1 and x2, so it has 2 features. Okay, it doesn't matter what those features mean. And features x1, it ranges from 0 to 5, and then x2 ranges from 0 to 3. Okay, so that's the original scale of the data. So the first step to normalize your data is to subtract the mean of all your to all your examples. So you're going to get every example xi, and you just subtract that xi by the mean of the whole data set. Okay, so the mean is is actually defined here, is 1 over m, right? Sum of all the xi's. And xi is a vector here, right? So we are summing m vectors and dividing by m. So the result mean here is a vector. So this mean is not one single value, okay? It's a vector because we have x1 and x2, so you're going to sum all these vectors that have 2 dimensions. The mean is going to be a vector that is going to be defined per axis or per feature. So you have the mean there is a vector where the first dimension is the mean of the first feature, and the second dimension is the mean of the second feature, okay? So you can do, when you do the subtraction here, xy equals to xy minus the mean, you're doing a vector subtraction, okay? And then you just have to divide by the standard deviation, okay? So now you get your xi and divide by the square root of the variance, right, which is the standard deviation, which is defined here, right? 1 over m sum of xi minus the mean squared. So the variance is the mean square error, right, with respect to the mean, right? So that's it. And then you take the square root because you want to be in the same scale of the data. So this is just, if you want to read the formula with xy divided by xy over sigma, that's easier, right? Sigma is standard deviation, okay? And then what you get is now, look when you do the first step, you're subtracting the mean. What you're doing is you're bringing all your data and centralizing it at 0. And then when you divide by the standard deviation, now both x and y here, or both x1 and x2, they have the same variance, which is 1. Okay? So here and here. And then you have this very nice looking data set that is centered at 0 and has variance 1. And this is it for normalizing the data. So when you have a data set, doing that almost never hurt. So it's always a good idea to do this. This is never going to make your learning harder. And when you actually have a data set with these very different ranges, this is very important. This is very, very important. Also, it's important to note that you have to use the same mu and sigma here, mu and sigma, for all your data set splits. So training, validation, and testing. You shouldn't split and then compute the means and variances for each split, because they will be different. And then you're going to rescale your data differently. So you would get different looking distributions here. What you want to do is normalize first, then you can do the split, and you're good to go. Okay? Just make sure you do that. Don't compute this after you split and then have different means and standard deviations for each split. Okay, and here's an example in NumPy of how to normalize now images using this concept. We can normalize images divided by 255, but you could instead actually apply this idea that we just discussed of subtracting the pixel values by the mean and divide by standard deviation. Okay, that's what you see here. And here you can see that there is an if-else here, because in images you can do that in 2 different ways. You can average across channels and then have a mean and standard deviation across all the 3 channels, or you can do that independently per channel. You can take the average and standard deviation independently for each channel, and that would be the implementation at the bottom. Okay, so this brings us to a more fancy approach, and this is called batch normalization. And this it's a very modern thing. It's from 2015, from this paper, Batch Normalization, Accelerating Deep Neural Network Training by Reducing Internal Covariate Shift, published at ICML, or International Conference on Machine Learning. So here's the motivation for batch normalization. When we do input normalization, what we're doing is, so we're rescaling your data and getting that very nice looking loss curvature, okay? But that only helps your first hidden layer. Because that doesn't guarantee that the activations of the next hidden layers will be normalized. Okay? So the whole idea of batch normalization is actually to normalize the activations inside the network, to make sure that after every hidden layer you get your activations rescaled, and that whole so by rescaling and normalizing all your layers, the whole training will become much faster and more stable, numerically speaking as well. Because the gradients look much nicer when you have this. Well, in general, you can think about this, right? Intuitively, if your loss curve is easier, that's easier to navigate on that curvature, the faster the algorithm is going to work. When I say the algorithm, the gradient descent is going to work, and the easier it would be to find the minimum of that function. So the intuition here is try to make that function, that loss function, a little bit easier. Okay. So here's how you compute or how you implement batch normalization. Let's go slowly here because we have to remember the notations. Right? So, and one key implementation detail here that we have to keep in mind is that even though the batch normalization is meant to normalize the activations, in practice, it's much more common to normalize the linear outputs of the layers instead of the actual final activations. So they normalize the Z's as opposed to normalize the A's. Okay? Let's keep these equations on the board because that might help us. We normally have, in a neural network, we have something like this, right? The Z of layer 1 is W1 X plus B. Let's assume this is one example only. Actually, no. Let's do, this should be a vector, and this should be an X matrix. And then we have activation 1, which is G of Z1. Okay? And let's actually, to be even more consistent with what we have been doing so far, is we've been mainly working with mini batch gradient descent. So you're going to have an XT here, okay, which is a subset of our data set. And what I'm saying here is that normally they normalize this value here as opposed to this value here. Okay? There's a debate, actually, in which one is better. But in practice, I think most libraries and most people implemented this by normalizing the Z's. So Z square brackets I refers to the linear output of the layer I, right? And then the rounded, or the parentheses there, they actually represent the example index, right? So here in this image, when I say, for example, Z1I, right, I mean a vector Z that has the outputs for each example I. Okay? So if I had 3 examples in my data set, x1, x2, 3, and x3, 3. Okay, so now, and just to not make this matrix squared, because that might confuse you, I'm going to add a 4th example. So now we have m equal to 4. We have 4 examples here, right? we have a W matrix, which is, so our W1 is a matrix that is 3 by 3, right? So the resulting matrix, right, Wx, and I'm doing this just so we know that the Z1 would be, so Z1, Z2, Z3, and Z4. Okay? So we're going to sum all these 4 Z's. They have the same dimension, right? So we can sum all these vectors. We're going to sum. This is the sum part. Then you divide by M. This is our mean. So we have a vector that is a sum of these 4 Z's that we divide by M. And then we do the same for the variance. But now we have the mean, right? So we computed the mean in the previous step, so we have the mean. So what you're going to do is, we're going to sum now these 4 vectors, but subtracting the mean for each one of them. So you're going to do minus the mean. It's going to be hard to minus the mean, minus the mean, minus the mean, minus the mean. And all of this squared. And then we sum the 4 of them, which is still a vector. This is a vector. So this is a vector minus a vector, which is a vector, squared is still a vector. This is a vector minus a vector, squared, still a vector. All these 4 will be a vector. We're going to sum all of them. And then divide the whole thing by n. That's our variance, sigma squared. And then the third formula is, we're going to now, for each of these vectors, we're going to subtract the mean, divide by the square root of sigma, and then sum epsilon. And here's the element-wise division, right? Okay. So maybe this makes you more interested in practice when you are working with PyTorch nowadays. You can just add a layer that is a batch normalization layer to your model, and that's it. So all that I said is implemented in these 2 layers here, batch norm 1D and batch norm 1D here. They implement those equations that I just said. And the name again is called batch normalization because you're normalizing across batches. That the average that we're computing is computed across the examples of your data. Okay, so we are averaging across the examples. Okay. So, but anyways, here is a simple multi-layer perceptron written in PyTorch. Right, this is a class called MLP, and it extends the module class of PyTorch. You're going to need to use this for this assignment. That's why actually I want to put it here. You're going to use a very similar thing to implement your convolutional neural network in the current assignment. So you have to define the init function and the forward function. The init function initializes your layers. And here I'm making it fancy because I have that sequential kind of meta layer that is just a sequence of layers, right? But it's a sequence of layers. The first one is a flattened layer, which is a special layer for flattening the input. I'm assuming we are dealing with images here. So this is going to flatten the images for me. Then there's a linear layer. And here is a fully connected layer that is assuming an input that is 28 by 28 with the MNIST images, right? And 64 neurons. So input is 28 by 28 and output is 64 size. And then when you're defining your batch normalization layer, you have to match the number of units, okay, of your previous layer. So see that the outputs of the previous layer it has 64 as 64 units. So my batch norm 1D here also has a 64. And the same for for the next linear layer here. Okay? So in practice, you don't have to worry about those equations. Okay? And you can do the same thing, but across the layer as opposed to across the examples. So before, our m there was equal to 4 because we had 4 examples. And if you think about this, 4 is actually a good example because 4 is a very small number for a batch size. Right? Imagine if you're dealing with 5 million images, you would take just 4 of those 5 million images to update your weights, and then go to the next 4 and the next 4. So because the batch size is too small, the average is actually noisy. So because of that, people have tried a different type came up with a different type of normalization, which is normalizing across the layer. The idea is exactly the same. It's the same equation, same thing. I still have alpha and beta here, still learnable parameters, but I'm just taking the average across a different axis. I'm not now averaging across examples of the mini batch. I'm averaging across the units of my neural network. And it is kind of confusing to understand this equations because there's too many superscripts and subscripts and brackets and whatnot. And it's tricky when you're dealing with neural networks. It's hard to formalize in a very clear way, okay? So I really encourage you to maybe look at the code and do it one example by hand if you want to get more familiar with these ideas. And particularly layer normalization, it's very important nowadays because it's there inside the transformer. So there is layer normalization in a transformer block, and you guys will have to implement this anyways, okay? Because this part you won't be able to use from from PyTorch. And then eventually you understand what's going on here. It's not very complicated. It is just rescaling the z's with a different mean and a different variance. And these mean and variance is defined by learning, right? While you try to minimize an error. And as I said, why not use just batch normalization? Because batch size might be too small, and then the average doesn't help much, right? Let's see. Okay, I think we should stop. Maybe we can look at some code in this last 20 minutes.